All right, so let's look at a few examples of performing t-tests to test hypotheses about a single population mean when we don't know the population standard deviation. So this goes back to example 4.2. So a company that packages salted peanuts in 8-ounce jars is interested in maintaining control on the amount of peanuts put into jars by one of its machines. Control is defined as averaging 8 ounces per jar and not consistently over or underfilling the jars. To monitor this control, a sample of 16 jars is taken from the line at random time intervals and their contents weighed. The mean weight of peanuts in these 16 jars will be used to test the hypothesis that the machine is indeed working properly. If it is deemed not to be doing so, a costly adjustment will be needed. So we've seen this example before, but when we tested the hypothesis before, we assumed that we knew the population standard deviation. And in fact, we used historical information about the standard deviation of fills by the machine to use in performing the hypothesis test. And that assumed standard deviation was 0.2 ounces. But if the process is out of control, if the machine is not working properly, so that the mean changes, wouldn't we expect that perhaps the variability associated with the fills is also changing? In fact, that's one of the definitions in many situations of a process that's not in control or out of control. The variability associated with what that process is doing increases. So, assuming that the population standard deviation is 0.2 ounces still, when there's a possibility that the machine is out of control, is probably not a very realistic thing to assume. So we're going to perform this hypothesis test without making that assumption. We're going to let the data inform us as to the level of variability that exists. So for a particular sample, here are the weights that we got. And so we have 16 values, and you can see those there on the screen. And so the question is, given these data, is the machine in control? Is it working properly, or is an adjustment necessary? And we're told to perform this test using a significance level of alpha equal to 0.05 or 5%. And remember, just to help refresh our memories on this, the alpha level, the 0.05, this is the probability of a type 1 error. A type 1 error is rejecting the null hypothesis when the null hypothesis is true and should not be rejected. In the context of this situation, a type 1 error would be if we shut down the machine unnecessarily. And so what we are doing here is we are setting up our test, setting up our decision procedure in such a way that there's only a 5% chance that we will reject the null hypothesis when in fact it's working, the machine is working properly. All right, so let's continue on. So we are going to set up the hypotheses, and again, before I proceed, I'm going to define the notation that I'm going to be using in setting up my hypotheses. I'm going to let mu represent the mean, the population mean weight in ounces of peanuts being dispensed into these 8-ounce jars by the machine. So this is a population or process mean, and that is the quantity about which we want to make a decision. The null hypothesis corresponds to our assumption that the machine is in control, that it's working properly. So mu is equal to 8. And we're going to let the data try to convince us otherwise. In other words, that mu is not equal to 8. And so we're putting that in the alternative. All right, we're wanting to try to show that the mean of the population is not equal to 8. And remember, we always put what we're trying to show in the alternative. Again, we've been told to use a 0.05 level of significance. And then I'm going to just help keep organized. I'm going to write down the formula for the test statistic. All right, so tcalc is equal to the sample mean x bar minus the hypothesized value of mu. All right, and we see that the hypothesized value in the null hypothesis is 8. And so I put that there. Don't put mu naught here, put the value. And then I divide that difference by the estimated standard error of x bar, which is the sample standard deviation s divided by the square root of the sample size. Now let's determine the rejection region for the test. Remember that we're using a sample size of 16 observations, and so the number of degrees of freedom that we have for this test is n-1 or 15 degrees of freedom. And so we have a two-sided test because we have not equal to in the alternative. And this is a t-test because we're using the sample standard deviation in the denominator of the test statistic. And so we're going to need the upper, let's see, we need to take this significance level of 0.05, and because it's a two-sided test, we need to divide that alpha by 2, so 0.025. And so we need to get the upper 2.5 percentage point of the t-distribution with 15 degrees of freedom. And so let me see here, let me bring that t-table back up again. And so we're working with the t-distribution with 15 degrees of freedom. You see it there. And we need to find the column for a right tail area of 0.025, and that's right there. And so now we go down to the row for 15 degrees of freedom. That is the value that we need to define the rejection criteria. Okay, so that upper 2.5 percentage point of the t-distribution with 15 degrees of freedom is 2.131. Okay, so again, because it's a two-sided test, we're going to reject the null hypothesis if our test statistic is either really small or if it's really big. How small does it have to be? Well, if t-calc is less than negative 2.1314, or if it's greater than positive 2.1314, then we're going to reject the null hypothesis. Now, I want to point out here a little bit of a difference between what we saw in the t-table and these values here. When I wrote these notes, I was using a t-table that went out to 4 decimal places, but that's really not necessary. In the table that I created for this class, I only go out to 3 decimal places, and so it would be 2.131 if we round these to 3 decimal places. So that's the little bit of a difference, so don't let that throw you. I was just using a different table when I wrote out these notes. So we've set up the procedure that we're going to use to test this hypothesis. We're setting up the protocol, if you want to call it that. Now, to go any further, though, we need to have our data, which we do. That's on the previous slide. And we need to start calculating summary statistics. Okay, so for that sample, we see that the sample mean is 7.8925, and the sample standard deviation is 0.1782. Again, the sample size we're using is 16 observations. And so we plug in the sample mean in the numerator, we plug in the sample standard deviation and sample size in the expression in the denominator. And so when we do this calculation here, we get negative 2.4130. And now to evaluate that value for the test statistic, we compare it to our critical points. And we check to see whether either of these two rejection criteria are satisfied. And since negative 2.4130 is strictly less than negative 2.1314, we would reject the null hypothesis and therefore conclude that the population mean is not equal to 8 ounces. To translate this conclusion back into the language of the problem, we would say that there is sufficient evidence at the 0.05 level of significance to conclude that the average weight of peanuts being dispensed is not equal to 8 ounces. Therefore, the machine should be shut down and adjusted. So when we state our conclusions in the language of the original problem, when we talk about there being a sufficient amount of evidence, we always have to say at what significance level, right? And we'll see why in just a second. Since we're using a 0.05 level of significance, we would say that there is sufficient evidence at that 0.05 level of significance to conclude that the null hypothesis is not true. In other words, that the average or mean weight of peanuts being dispensed is not equal to 8 ounces. Let's calculate the p-value for the test. Because we're performing a two-sided test, the formula for the p-value is 2 times the probability that a t-random variable with 15 degrees of freedom in this case is greater than or equal to the absolute value of the calculated value of the test statistic, which was negative 2.4130. And so we have to take the square root of that. I'm sorry, not the square, the absolute value. And so we get a positive 2.4130. And so the p-value is equal to 2 times the probability that a t-random variable with 15 degrees of freedom is greater than or equal to positive 2.4130. Let's go back to the t-table. And so this is, again, we're dealing with the t-distribution with 15 degrees of freedom. Notice that we only have percentage points for a very small number of right tail probabilities. we don't have the level of granularity or the level of detail regarding right tail probabilities and the corresponding upper percentage points as we do for the standard normal. And so we're not going to be able to, at least using the t-table itself, we're not going to be able to compute the p-value for a t-test exactly. Now, if you're using computer software, as you are in the lab for the course, then that's going to be able to give you an exact p-value. But when we're using the tables, the best we can do is get an approximation to what that p-value actually is. But sometimes that's all we need. So again, we want the probability that a t-random variable with 15 degrees of freedom is greater than or equal to 2.4130. And so let's see here. This is the row we're dealing with right here. Now, if we look for 2.4130 here across this line, we don't see it. It's not here. But we do see two values that bracket the 2.4130. We see 2.131 on the lower end and 2.602 on the upper end. And so what we can conclude is that, well, let me back up a second. We know that by definition of what these values represent, the probability that a t-random variable is greater than or equal to 2.131 is 0.025. And we know that the probability that a t-random variable with 15 degrees of freedom is greater than or equal to 2.602 is 0.01. And so therefore it follows that the probability that a t-random variable with 15 degrees of freedom is greater than 2.4130. Just check on that. Yeah, 2.4130. We know that that probability has to be between 0.01 and 0.025. And so that is the basis for what I've got written right here. Based on our t-table that we've got, we know that this first component that we need for the p-value, the probability that a t-random variable with 15 degrees of freedom is greater than or equal to 2.413 is between 0.01 and 0.025. Now we have to multiply that by 2, and so that implies that the p-value, or twice this probability, is between 0.02 and 0.05. All right, so the p-value for the test, using this t-table, the best that we can discern is that the p-value for the test is strictly greater than 0.02, but strictly less than 0.05. Now, remember that when we're doing a hypothesis test, we don't have to use both the test statistic and critical point method and the p-value method. We can use either. I'm showing you both here so that we can understand how they're used, how they're calculated, and then how they're used. So if we were going to use this p-value to decide whether or not to reject the null hypothesis, remember that the way we use it is that we reject the null hypothesis if the p-value is less than or equal to the significance level being used. So since the significance level we were told to use in this example is 0.05, since we've concluded right here that the p-value is strictly less than 0.05, and so based on the p-value, we would reject the null hypothesis and conclude that the alternative is true, which says that mu is not equal to 8 ounces. And so again, we would, based on using the p-value method, we would draw the same conclusion. There is sufficient evidence at the 0.05 level of significance to conclude that the average weight of peanuts being dispensed by the machine is not 8 ounces. All right, now one more question for you here. What if we were to use a significance level of 0.01 instead of 0.05? What would our conclusion be? Well, there are a couple of ways we can approach this. We could look up the critical points for a significance level of 0.01, or we can use the p-value method. And the p-value method is going to be easier to use here because all we have to do is compare that p-value to the significance level. Now remember that on this previous page we concluded that the p-value is strictly greater than 0.02. Now if the p-value is greater than 0.02, it cannot be less than or equal to 0.01. So if we were to use, instead of a 0.05 level of significance, we were to use a 0.01 level of significance, then our conclusion would be different. The conclusion would be that there is insufficient evidence at the 0.01 level of significance to conclude that the average weight of peanuts being dispensed is not 8 ounces. We would not be able to reject that null hypothesis in favor of the alternative if we use a 0.01 level of significance. So the bottom line here is that we're seeing that the conclusion that we draw depends on the significance level that we use. In this data, there's sufficient evidence at the 0.05 level of significance to reject the null hypothesis, but there's insufficient evidence at the 0.01 level. And so this demonstrates using a smaller level of significance corresponds to demanding more evidence against the null hypothesis in order to reject it. So this is a very important point to see here, that the conclusion that we draw depends on the level of significance that we are using for the test. All right, well, let's look at one more example here. An apple buyer is willing to pay a premium price for a load of apples if the apples have an average diameter of more than 2.5 inches in that particular load, in that particular shipment. The buyer wants to test the claim of sufficiently large apples, so he takes a random sample of 12 apples from the load and measures their diameters, and the results follow. So here we have the measured diameters of 12 apples that were selected from the shipment. So the question is, should the apple buyer pay the premium? Well, okay, let's think about this for a second. He only wants to pay the premium if he can conclude that overall in the entire load that the average diameter of the apples exceeds 2.5 inches. But obviously nobody has time to take every apple in the shipment, measure the diameter, and calculate the population mean diameter. Nobody's going to have time for that. So the apple buyer has to make a decision based on a sample from the population. He or she would be able to do this very quickly because they only have to measure 12 apples. And so should the apple buyer pay the premium? Well, this is a statistical question. We have to draw an inference about the entire load or shipment of apples based on this very small sample. And we're told here to perform the test using a significance level of 0.05 or 5%. All right, so we would need to eventually calculate the summary statistics for this sample. All right, so now you'll see here, by the way, that I'm in writing up this example, I'm using one of the templates that I provided for you on Moodle to help organize your work when you're doing hypothesis tests. This is the outline format, so I would encourage you to start using these to help solidify the process in your own mind of how we do hypothesis tests. You can see here that the procedure stays the same from one kind of hypothesis test to another. The only difference is in the parameters that we're making or testing hypotheses about, the formulas for the test statistics, the rejection criteria, and so forth. All right, so for this example, first I'm going to define the notation to be used in setting up the hypotheses. And so I'll let mu denote the mean diameter of apples in the entire shipment. The buyer wants to see, is there enough evidence to show that mu is greater than 2.5? The buyer is not going to pay the premium unless there is sufficient evidence to indicate that the premium should be paid. All right, and that corresponds to mu being greater than 2.5. So that's what he or she is trying to prove. So we're going to put that in the alternative hypothesis. We'll put the opposite of that in the null hypothesis. And so the apple buyer is going to assume that the average diameter of apples in the shipment is no more than 2.5 inches, and the buyer is going to let the data try to convince he or she otherwise. Okay, we're told to use a 0.05 level of significance. The test statistic, well, we're using a t-test, so it's x bar minus, and then notice that I'm not putting mu 0 here, I'm putting the actual value. Don't put mu 0 here, put the value. And then I divide that difference by the estimated standard error of x bar, s over the square root of the sample size. Notice that when I write down just the formula for the test statistic, I'm not doing the actual calculation out here. And I'm also not putting in values for x bar and s. Because again, as I think about this, we can go all the way down to defining the rejection criteria without having collected our data. The steps down to this point were essentially defining the process or protocol that we're going to use to test the hypothesis. So we don't need data until we want to go further than this. The reason I have students write out the formula is so that if they get something wrong down below, I can at least give them partial credit if they've got the test statistic formula correct. We need to define the rejection rule or the rejection criteria. Now, this is a right-tailed test. if you look at the alternative hypothesis, the inequality is pointing to the right. So this is a right-tailed test. That means that we're going to be rejecting the null hypothesis for large values of our test statistic t-calc. Now, how large does t-calc have to be? Well, it's got to be greater than the upper fifth percentage point of the t-distribution with how many degrees of freedom? Well, n minus 1. The sample size is 12, so we have 12 minus 1, or 11 degrees of freedom. And so the critical point is the upper fifth percentage point of the t-distribution with 11 degrees of freedom, which, if we go back and look at the table, right, so here's 11 degrees of freedom right here, and we want the upper fifth percentage point, so 1.796. So rounded to 3 decimal places, that's what it is. Again, when I wrote these notes, I was using a table that went out to 4 decimal places, but again, that's really a little bit of overkill. We don't need that level of precision here. All right, so then to go further, I've got to calculate my summary statistics for my sample. In particular, I've got to have the sample mean, I've got to have the sample standard deviation, and the sample size. And so the sample mean is 2.7583 inches. Remember, the data here are inches. And the sample standard deviation is 0.3942 inches. All right, now I know that I've got probably more digits here than I need, but I like to go out to the several decimal places here so that I don't incur too much rounding in my test statistic. We can always round it later if we need to. So plugging in the value for x bar and the value for the sample standard deviation and for n in this formula, but we do it down here, all right, we get a calculated value for the test statistic of 2.2699. Now, to evaluate that, we compare it to our critical point, and we see that 2.2699 is greater than 1.7959. So because of that, we reject the null hypothesis and conclude that the alternative is true, which says that mu is greater than 2.5. So to translate this back into the language of the problem, we would say there is sufficient evidence at the 0.05 level of significance to conclude that the average diameter of apples in the shipment is greater than or exceeds 2.5 inches. And therefore, the buyer should go ahead and pay the premium. All right, so we performed this test using the test statistic and critical point method, but we could also test it using the p-value method. And so let's see how we would do that. Now again, when you're doing a particular problem, don't do both, right? You only need to do one way. You'll get the same answer regardless, but I do want to give us practice in seeing how these calculations are done. So for a right-tailed test, the p-value is equal to the probability that a t-random variable with n minus 1, or in this case 11 degrees of freedom, is greater than or equal to the calculated value of the test statistic. Now the calculated value of the test statistic was 2.2699, and if I go to my t-table, again I'm in this row corresponding to 11 degrees of freedom, and I see that the value of the test statistic is between 2.201 and 2.718. And so the probability we're looking for, we know, is between 0.01 and 0.025. And so we can conclude based on this that the probability that a t-random variable with 11 degrees of freedom being greater than or equal to 2.2699 is greater than 0.01 but less than 0.025. And so that implies that the p-value is greater than 0.1 and less than 0.025. And since the p-value, if we were using the p-value method rather than the test statistic and critical point method, because the p-value is indeed less than or equal to 0.05, right, because it's less than 0.025, so since the p-value is less than or equal to 0.05, we would reject the null hypothesis and conclude that the alternative is true. Now, again, let's consider what if we were to use a significance level of 0.01 instead of 0.05. Well, on the previous page, we saw that the p-value for this test is strictly greater than 0.01. And so it's not the case that the p-value is less than or equal to 0.01. And so because of that, because the p-value is not less than or equal to 0.01, the conclusion at the 0.01 level of significance would be that there is insufficient evidence at the 0.01 level of significance to conclude that the average diameter of the apples in the shipment exceeds 2.5 inches. So if the buyer were using a 0.01 level of significance, they would not pay the premium because there is insufficient evidence at that level of significance to conclude that the average diameter in the shipment exceeds 2.5 inches. So we can see here again how the decision that we draw, the conclusion that we make from the data, depends on the level of evidence required in order to reject the null hypothesis. And the level of evidence required is related to the significance level that we use. The larger the significance level we use, the less evidence we're requiring against the null hypothesis in order to reject it. The smaller the significance level we use, the more evidence we're requiring against the null hypothesis in order to reject it. So that wraps up this subsection in making inferences about a population mean when the standard deviation is unknown. We're going to move into talking about confidence interval estimation for a population mean in that context. So that will be in the next lecture. So I'll see you then.